Hello and welcome to the Geodynamo Lab here at the University of Maryland. First thing you see when you walk in is this giant cube which houses the experiment, as well as some nitrogen tanks. Over here we have an empty tank which will eventually be filled with sodium. And further back we have a shed which houses the controls for the experiment as well as graduate students. Now if we squeeze in here, which we can, because it's just me, we can get a closer look at the experiment. So this is the 3-meter spherical Couette liquid sodium magnetohydrodynamic experiment. So let me break that down for us. It's 3 meters across in diameter, and it's spherical. We have this outer shell, spherical shell, and inside we have an inner sphere whose radius ratio is comparable to Earth's outer core boundaries. When we run this experiment, the Couette part indicates that we have boundaries, concentric boundaries, that are differentially rotating with respect to each other and acting on a fluid sandwich between them. So this is how we create turbulence in the experiment. And when the experiment runs, these inner and outer shells will independently rotate. And for example, this outer shell can rotate at a rate of 4 hertz, so that's 4 revolutions per second. So what happens is then the fluid predominantly wraps around in this direction. So when the experiment's running, since it's so fast, this door will be closed and we're all safe in the shed. The fluid, yes. So the fluid is liquid sodium. So right now it's at a solid state, but it's heated up. It's hot, not too hot, about 115 degrees Celsius. It's just so that it's liquid. And when it's liquid, it's not very viscous. It's the viscosity of water almost, but we never mix it with water. That would create fire. Hence the nitrogen gas to put out for safety. And we don't have any sprinkler systems in this lab. So while the experiment differentially rotates, we also have a magnetic field applied by these 2 electromagnets situated here and here on the upper and lower hemisphere. So we run a current either in the same direction or opposite directions to generate different magnetic fields. And that magnetic field passes through the air, through the stainless steel shells, and through the liquid sodium within. And because of the wrapping motion of the fluid, we also have that magnetic fields will wrap predominantly in this direction. But what we want to see and what we want to achieve is dynamo action, where the magnetic fields actually recombine with the applied magnetic field and will wrap instead in this direction. So this calls for some changes in the experiments so that we achieve those dynamics. So currently we are undergoing some upgrades to the experiment to try to get more of the magnetic field flow in this direction. So the next part, I'll go to the top of the experiment and I'll talk about measurements and actually show you some of the sodium. But let me just point out one of the devices we use in measurements of the experiment. Here, you can kind of see, is a Hall probe right there. And this measures the magnetic field, a component of the magnetic field on the surface of the experiment. All right, so let's go to the top. So here we are at the top of the experiment. The clip I showed before I had recorded some time ago. It actually showed that there was an inner motor on top of the experiment, which would be placed right here. And the thing we didn't see is there's also an outer motor that would be around here, which are used to rotate the shells independently. So those have been removed so that we can work on the upgrades and replace the nitrogen tank for safety. So measurements. Some of the measurements we take on the experiment are torque, so the torque both by the inner and outer motor, as well as pressure sensors. And what I'm most interested in is Hall probes. that measure the surface magnetic field, just the radial component of the magnetic field, that is the component coming out from the origin. So what I'm looking at through simulations is trying to understand the best placement and as well as the number of Hall probes in addition that we should add to so that I can best predict the magnetic fields using data simulation and machine learning techniques. Another type of measurement that we are working on right now is acoustic Doppler velocimetry. So if you're in seismology, you might be familiar with this kind of measurement, but we currently don't have a sense of what the velocity field is doing inside. So we'd like to use acoustic Doppler velocimetry to help fill in some of that information we do not have. So the last thing I'll show up here is what the sodium looks like. So we usually don't have a viewing port on the experiment because we want it to be very contained. But as we make upgrades, we need to see what we're doing inside as we remove this inner shaft and inner sphere. So you can actually see the sodium today. So I'll pick you up. Go over here. So here is the port. And if you look inside, if I angle it right, you can actually see some of the sodium within. It's kind of a grayish color. And right now it's at a solid state, it's not melted. And the texture is kind of like cheese. So if you cut into this, well, the surface is kind of a little bit more oxidized, but deeper into it, it's more of a darkish metallic gray. So the last thing I'm going to do is we'll head downstairs and I'll talk about what we're doing in the upcoming upgrades. So in the last part of the tour, I'll be talking about some of the upgrades we are going to be doing for the experiment. So currently, Ruben Rojas and Artur Kurevalov are working on adding what are called baffles to the inner sphere, because I mentioned we get a lot of flow wrapping around in this direction, but we want to see flow moving in this direction. So this is just one of the prototypes they were looking at. So this is not the exact one they chose. The exact one has more like an arrow shaped along the equator. But this is one of the ones they tested in water experiments to see that flow started to go in this direction more. The other thing we are testing, actually using this sodium tank, is the possibility of adding acoustic Doppler velocimetry. So you can see on two of the ports we have a speaker as well as a microphone, so we could test that. So the procedure is going to be this. We'll first heat up and drain the sodium from the 3-meter experiment into this tank. Remove the inner shaft and inner sphere. Add the baffles to the inner sphere. Put that back into the tank, or put that back into the 3-meter outer sphere. Then we'll heat up the sodium that's in this tank by running hot oil through this dimple jacket here and pour it back into the experiment. Cap the experiment again and spin it up, get it running. So hopefully we'll be running in 2021, but that concludes the lab tour.